of velocities of particles will follow a Maxwell-Boltzmann distribution. So far, so good, I think. So integral of that Maxwellian is the density. Basically, how wide it's centered on the velocity, the mean velocity of the flow is the mean velocity of the particles, and how wide it is the temperature, given by the temperature, which gives the thermal excitation. And then from this, we can reconstruct mass, so density as the zeroth moment, momentum as the first moment, and energy as the second moment. Okay? And then LBM does a very gross discretization of the velocity space. So this is the key point of LBM. So here I'm illustrating it with a 1D framework. So here I've discretized the 1D space in velocity space with 3 velocities. Basically, I'm not entering in the details, but we reconstruct it using Hermite polynomials basis, okay, that allows quite naturally to link the Maxwellian shape with transforming it into these polynomials, which allow an exact quadrature up to a certain order, in that case, order 2. And so instead of now having moments which are going to be linked with integrals of f, of course, we have moments that are going to be some sums, okay? So this is the moment. So order 0 is nothing but the sum of fi. In that case, I have 3, okay? And then order 1, so rho u alpha would be sum of ci alpha fi, okay? I changed ci alpha to ci alpha because there's a non-dimensionalization process, okay? But it's still the velocity of the particle. Now, if we rewrite the previous system, we have exactly the same equation. I forgot to mention before, this was the external force. So I dropped the external force for this. And now we only have n, being the discrete number of discrete velocities, n equation on discrete fi's. Okay, and so you see that this is nothing but a convection equation with a relaxation term here, which is going to relax to the equilibrium. What's really important in the construction of LBM is that this Ci alpha stems from the psi alpha, the molecule. And so this is the discretization of velocity space, and it's going to be constant everywhere. So this is the big change with the classical methods, is that we have a convection at constant velocity. Now, if we do some math from this, okay, I can also do it directly from Boltzmann equation, but you can do some math from directly the discrete velocity Boltzmann equation. You can show that this is equivalent up to second order in space and time to this equation, okay? So what we have is a derivative of moment n, d dt, moment n, plus divergence of moment n plus 1, okay? So I said that moment 0 was density for f. Moment 1 is rho u alpha. So you can see already that here you have the continuity equation in order 0 given, and that's a constraint, that the collision conserves mass. So that's the case, okay? Same for the second order. First order, you're going to have rho u alpha here, and here you're going to have rho u alpha u beta plus p Kronecker delta alpha beta. So if you construct well the moments of your equilibrium function, then you can recover like that a cascade of equation. And that's how you reconstruct all of your quantities. So once you solve for f, then you can reconstruct for density, for momentum. So if we do now, there's one last trick, and this is the most important one. In 1D, it's easy to see. Through non-dimensionalization, we set the discrete Ci alpha, in that case. So the velocity for 1 here is exactly delta x over delta t. Okay, so delta x is going to be constant, at least locally. So I'm talking about a Cartesian mesh here. And delta t also constant. So this is a big constraint for what we're going to do later. Okay, so delta x and delta t are linked automatically via the choice of discretization that we made from the start. Okay, so I'm discretizing the velocity space, and then I have my delta x and delta t. But what's beautiful about having constant convection with delta x over delta t is that if you consider that this one is f1, the only thing it does during one time step is that it jumps to the next grid point. Okay, so you don't have to solve for convection, it's exact. You're just moving the fi's in the direction of the lattice. Okay, so you have one that's just standing here, the zeros, it doesn't move, will be modified by the collision only, and the +1 goes to the right and the -1 goes to the left. So if we do that in 3D, it's exactly the same principle. The only trick is to consider a set of discrete velocity which are going to be embedded in some cube. Okay, so if I do it in 3D, I have the most common one is D3Q27, which is going to point from 0 to all of the neighbors, okay, including all of the diagonals of the cube. So you have 8 in 1D, so times 3, plus, wait, no, you have 9 with this one, 9, 9, 9, so D3Q27, okay? So when you say D3Q27, the D3 is for 3D, and 27 is the number of discrete velocities. In what I'm going to present, we use a slightly shorter lattice, which is D3Q19, so I don't have the corners of the cube, so I only have 19 velocities. The same idea. And just the same, each velocity points exactly to the next point, okay? So when I'm going to solve now my DVBE, now I only have 2 steps, okay? What we call streaming. So streaming step is nothing but moving the data around, so moving the fi's to the next grid point in the direction of its discrete velocity. And we have a collision here, which is going to be local. It's very important, and it's going to relax towards the equilibrium projected on the basis that we're considering. And the equilibrium, in its simple formula, looks like this. Okay, so it's projected on the Hermite basis. So once you've done the 2 steps, which actually, as you can see, write an equation as 1 step, then you can reconstruct density, rho u alpha, and this is the second order that allows you to get the right momentum flux, okay, in the second order equation. If you have any question on this, I can answer. So this is a very basic LBM. Perfect. And then you can do this, okay, almost straightforward. So just to mention that it looks like when we write this, it looks like we're doing a first order Euler integration. So can say that this is first order, but in reality what's hidden behind is a Crank-Nicolson scheme, so it's actually second order. The scheme is second order in space and time. Okay. So there is one problem with what I showed here, is that this works very well to solve isothermal flows, okay? And isothermal flows in which we assume P equal to rho Cs squared, so sound speed square, okay? So this is the classical closure if you have constant temperature. But there is one problem with this framework here that I'm describing, is that if we consider the energy equation, okay, energy equation should be order 2 here. So here should be order 3. And when we consider closest neighbor lattices, like this, okay, we always have plus or minus 1, basically. All of the velocities are plus minus 1 ordinates. And if you do that to the cube, you always get the same, plus or minus 1. This means that the third order, pi alpha alpha alpha, is equal to pi alpha, which means that your flux of energy is the same as the flux of mass, basically. It's linked. And so you see that you have a problem. That's why with the closest neighbor lattices, this kind of discretization, you cannot do compressible flows. You can only do weakly compressible, weakly in the low Mach limit of isothermal flows. Okay. So what I want to do, what I showed you on the first slide is this. So there's, we cannot do this with, obviously, with this equation. So I've shown you how to solve these two equations with Lattice-Boltzmann method. And now we need to find a way to solve all of the other methods, all of the other equations, sorry. And these are the classical combustion equation. So I'm not entering into detail, but basically we want arbitrary transport, arbitrary equation of state, arbitrary chemistry, arbitrary gamma, very importantly. In LBM, usually we have constant gamma, and so on. So difficulties that will arise for LBM is that we have much more conservation equation. For hydrogen, for instance, we have usually 9 species. No, it's dilatable compressible. And I didn't mention this, but we have variable gamma, which when we do the classical cascade of LBM, of the moments, we end up with a constant gamma, which worth is dependent on the dimension of the problem. So there are some fixes, but they're not so straightforward. So how are we going to solve for energy and species? There are basically two main options. The main option, so here I'm going to start first with the energy equation, so the compressible part. I want to solve the compressible part, and then I'm going to deal with the species. So when we want to add the energy equation, well, the most straightforward way is to extend the basis of velocities, discrete velocities I discussed, to avoid having that pi alpha 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 equal pi phi. So if we do that, we can develop what is called multi-speed Lattice-Boltzmann methods, and usually we end up with a quite large number of discrete velocities. And it has a number of problems, but especially it starts being quite expensive. So the gain that we usually have with LBM is not that clear anymore, because we're multiplying by 4 or 5 the memory that's required to do simulation, instead of, by the way, 5 equations in classical Navier-Stokes equation. Second idea is to do segregated method. So the first, I think this was historically the first idea. People wanted to stay in the LBM framework, so they said, okay, I cannot get energy as the second order moment of my distribution function, so I'm going to introduce a new one, which is going to behave exactly in the same way as the first one. It's going to be solved with the same algorithm, but energy now is 0th order, and I'm going to couple the two, basically, okay? This works. There are a number of papers, but it also gets quite expensive, especially if you want to consider n species, because then you need to have 19 for rho and rho u alpha, 19 for the energy, and 19 per species. It starts getting quite expensive. And when we think about it, the nice thing about LBM is that you can solve in the same equation the 0th order and first order, so mass and momentum equation. But after the first order, what would be the next order equation for energy, at least at Navier-Stokes level, there's none. So the only thing we want for this, from this, is the 0th order. Sorry, it's the sum of all of these quantities, GIs, typically, okay? So if I just want the sum, then I can just solve for the sum, which is one scalar. So that's what I developed in my team. So this is a class of hybrid methods. And in that case, basically, we solve for 19 discrete velocities, 19 FIs, and we add to our vector of unknown E, okay, for instance, E, we're going to discuss about which E, and the species. Okay, so we just add. So typically, if I want to do hydrogen combustion with 9 species, I need energy plus 9 species plus the 19, so I have 29 unknowns in total. Okay, so just a quick reminder of notations here. So we have a streaming step here in the LBM, which is streaming a colliding population, which can be written like this. So basically, this is an equilibrium. This is the Maxwell-Boltzmann function that we saw earlier. And this is an off-equilibrium part. This is nothing but F minus Fx. And this is if we have a forcing term. So we need to make some changes to get the dilatation right. Okay. So the first thing that we did, the most important, okay, is to introduce a parameter, theta, which is going to be some sort of reduced temperature, okay? So before we had P equal rho Cs squared, so theta equal 1, and now we want to have theta non-equal to 1. So this can also be seen as a ratio of sound speed squared to, a ratio of sound speeds, typically. Or ratio of reference temperature to a reference temperature. But this indicates this is my temperature variable, okay? This is now projected on my polynomial, so order 0 is always rho. This is non-negotiable because this is my mass. Here order 1 is rho u alpha, and now order 2 is not, here I used to have rho Cs squared. Now I do that times theta minus 1. So I get the right pressure into my momentum equation in the momentum flux. And then we actually extended this to third and fourth order, okay? And I'm going to illustrate why this is important for compressible flows. So fourth order is the most important. Fourth order actually controls the isotropy of the dilatation, which we didn't have in the classical Lattice-Boltzmann method. Okay, so we showed this is a very simple test case. This is a spherical flame. And you can see that with controlling the fourth order, you can prove that through a Taylor expansion, that you get a much better isotropy of the dilatation. You see that this is the same problem without that fourth order, and we get spurious currents so strong that we cannot sustain at all a physical solution. Okay, so of course this is very wrong. This is what we had some years ago. So this is for the fourth order. The fourth order controls the isotropy of dilatation, again, that we didn't have in the original LBM. The third order is a bit more sensitive, but third order controls the isotropy, for instance, in a jet. Okay, so we're all talking about errors here. I mean, every scheme, if I cut my F equilibrium to second order, I will be consistent to the Navier-Stokes equation. Okay, the problem here, what we're doing through third and fourth order, what you don't want is your error to be too different in the different directions, because after a long time, then you have you're in troubles. Okay, so this is what will give you spurious currents or this kind of behavior. So this is a jet. This is actually a 2D problem, but with 3 dimensions. So this is periodic in this direction, and I'm just looking at the evolution, temporal evolution of a jet-like. So there's a jet coming to me, okay, at max 0.9. And you see that here I have a lot of diffusion on the x directions. And so this destroys basically the structure of my jet. Okay, so this is the third order. So this is what we did for the LBM part. Okay, this is what we modified for the LBM part. Now I'm going to mention what we did for the species and for energy. So I'm going to accelerate a bit. Basically, what we want to do is that we know, at least I know, that LBM is very good at transporting vorticity and acoustics, especially acoustics, but vorticity on very few points also. So the idea is to keep within the Covassner modes, to keep vorticity and acoustics solved by LBM. And the next mode, we're going to do what we can, basically, initially. So if we consider any of these equations, okay, so this one for mass, this is just the Eulerian part, okay, I dropped the diffusion and source term. If I take any of these equations, so species, entropy, enthalpy, we have a characteristic equation. So small perturbation will be only convected at U. This is an eigenmode. It's a Covassner mode. Basically, when we solve this equation coupled with LBM, it's very easy because it doesn't sign on the other. It's a weak coupling with the other modes, with acoustic and vorticity. So basically, it doesn't perturbate the acoustic and vorticity. So to solve this, you can almost use any scheme you want. Let's say you can use central scheme or anything you want. The best always is to use this kind of isotropic finite difference scheme, because then you're using all of your neighbors, the same as the LBM. Okay, so this is what we're using, what we used to use at the beginning. This is very straightforward to do. So we're using, of course, it's, as I said, it's just adding scalars. So we're solving on the same grid, same time step, okay, as LBM. So it's everything is mono, it's one block of code. And then we developed new categories of schemes, also at the lab, based on early proposals here, which basically see on the lattice, basically everything, when we exchange the data, what I send to the next point and what I receive from the next point is the mass flux, exactly. The mass flux computed by LBM. So this is the mass flux, delta M, and I can reconstruct from that, if I multiply, let's say, the mass flux by a species, okay, whichever I can take the value from the neighbor, my value, center value, anything. Basically, this is going to be the species mass flux. So we can reconstruct a lot of numerical schemes like this, which are going to be consistent with LBM. Okay, so these are some examples for weakly compressible flows, but I'm not going to. I prefer to focus on the combustion. So this is the first steps that we showed, especially to the partners of the consortium. So these are the first simulation for compressible aerodynamics. So for this case, we're doing M6 wing, and you see that this is a transonic wing. So we have the shock here, and this is early work. So this was done with entropy equation. And also see that we had a lot of noise on the boundaries, because I'm not going to mention it, but since we have Cartesian meshes, we don't have a point exactly on the boundary. So treating the boundaries is quite complex. But these were the first compressible complex simulations that we did. This is a bit more recent, so we're considering a blade cascade, okay, LS89 for those who know. So this is a transonic configuration to mimic, say, what's in an aircraft engine. Okay. So again, if I consider the equations for entropy, enthalpy, and so on, for energy and species under non-conservative form, the ones I showed, I have a weak coupling, and it's quite easy to couple it with the LBM. I don't get problem, okay, because they are characteristics. So this is nice, and you can do a number of simulations. But, there's always a but, if we look at things which are more compressible, know that entropy equation is a bad equation, at least in that form, because the entropy is not conserved through shocks. And when we consider this, you see that if we do a SOD shock tube, we get here a wrong Eugenio condition across the contact and the shock. So this is bad. This is not bad for what I showed before, because it was transonic flow, so it was really, the Mach was really low. I mean, low, more than 1, but less than 1.2, let's say. And the effect of entropy on the jump condition is, it goes with Mach cube, if I remember well. So basically, you don't see it until you get a bit further in terms of Mach. But this is higher Mach. This is maybe Mach 2. So here we can start seeing errors, and this is not okay. So the reason for that, the reason for that is that in any conserved equation, so if I want to solve, let's say, total energy, which is the right equation to solve to get the jump correct, or same for the species in the conservative form, if I do this, then there's always, you know that if you expand your derivatives, you always end up with the mass equation, okay? That's how you get the non-conservative form. The mass equation has to be the same as the one that you're solving with the LBM. Basically, the scheme that you're using for energy equation or species equation needs to be consistent, but I mean, consistent is the wrong term, sorry, because consistent means that it has to be, that the mass has to be the same in the limit of small delta x, delta t. That's not what I meant. It has to be the same mass, because if it's not the same mass, then you get spurious current. And then it explodes, basically. So we developed another category of schemes, okay, always based on these mass exchanges across links, okay, to basically be able to transport directly the energy flux in the right form, so rho u capital H, so total enthalpy, which is conserved through the shock. And we made several proposals for this, but basically doing this will allow the scheme to recover exact Rankine-Eugenio relationships. And then you can go further in terms of Mach. Okay, so this is a number of examples. These are quite known. These are 2D Riemann problems. So on the left is the reference. On the center is using entropy equation. And you see that all of the results are wrong, basically, because the characteristics of the system are different. So we get very different results here also. And when we solve for total energy, we finally get the right patterns. Okay. So now I'm going to show some applications. Do you have maybe questions on the scheme that we're using? No more numerical schemes, promise. So back to my problem statement. So this is a test case that we did a while ago, but now maybe it will make more sense with some examples of what the mesh look like and so on. So I said the mesh is Cartesian. Of course, it's not Cartesian everywhere. If I want to do big industrial burners, and it is Cartesian locally, but it's an octree mesh, okay? So what happens is that you can define some mesh transitions, okay? And so you can basically deal with any type of geometry like this, okay? If you were careful, there's one thing that's not easy, is that here you are multiplying the delta x by 2, so you start seeing some filtering problems, but you're also multiplying the delta t by 2, okay? You're multiplying the delta t by 2 because delta x over delta t is linked with my discrete velocity space, and this is constant everywhere. Yes? So I have strong filtering problems here. which I could give another seminar, but this is not something I'm going to discuss today. Okay, so you just need to be very careful here. But the good thing about this also, and this is what is going to save us for the industrial cases, is that this also means that this grid is going to be doing one iteration, twice less iteration than this one, twice less than this one, etc. Okay? And so the numerical cost of one level of a grid is not linked to its size, okay, but to basically the number of points that I have in that grid, okay? And there's a 2 to the power n somewhere, because if I have, basically if I have only one very small point, very small grid point, it's going to cost me nothing because I'm not changing the time step elsewhere, okay? So I'm doing a constant CFL-like calculation. This is magical for industrial burners, because industrial burners, not so much on this one, but you have a lot of geometrical details that you want to account for, typically small injection holes and so on. And you don't usually need many points to solve them, because you cannot afford it usually, but you don't want to change the delta T everywhere else in your chamber, which is 15 meters, okay? So in that case, it solves naturally that problem. And so that's why we can do this kind of simulation for a very reasonable cost. This is actually one of the main reasons, okay? Which, by the way, is not limited to LBM. You can also do that with Octree Navier-Stokes. But the LBM is still, I mean, the algorithm itself is still faster, but where we gain most on industrial cases, I think, is for this reason. Okay, so then I developed, I showed you the scheme. So the scheme, we also have mass, momentum, energy, classical. So and the species and energy are written in a classical way. So basically, you can redevelop any type of boundary condition you like. For example, for combustion, we like non-reflecting boundary conditions. Usually acoustics, so you can do exactly the same. So everything else in terms of models is the same, okay? Source term is going to be tackled in the same way as in classical code. You just need to be careful because the time step is always the same. Okay, so you cannot negotiate with the time step. So typically the Fourier constraint, you need to make sure that it's satisfied on the side. Same for the chemical integration, unless you're doing implicit integration, for instance. But for Fourier, you need to check that the Fourier number is satisfied, because otherwise you're in trouble. But it's quite easy. It's quite easy. You can do it as post-processing. And you can restart your simulation, changing the time step, for instance. Basically, rescaling everything. So here we're using classical models. So we're going to use here a turbulent Riemann model for turbulence. Sorry, turbulent Schmidt and Prandtl number, and thickened flame model. We did that because a lot of people are using this model. Now we have a lot of other models. And you can use classical chemistry. So in that case, we're using two-step chemistry. And then you can do, same as usual, M0, M1, M2, some convergence study. And this is what the results look like. Okay, and then you can validate a good convergence, so between M1 and M2. So this is temperature, mean, and RMS. Compare with experiments, and our reference in that case is a simulation from the team of Vincent Moreau. Okay, so we have good agreement. The only slight discrepancies here are on the walls, but this is because back then we didn't have heat losses. So this was adiabatic versus heat loss simulation. So I'm going to illustrate some more cases. So this is a case of detonation. So it's exactly the same scheme. You can validate the ZND profile. Here, what I'm showing here, the only thing I want to show you is the sensor, okay? Because there's nothing free. It has most other codes. We don't solve, let's say, a Riemann problem or anything. So in that case, for now, and we're working on that, we need a sensor, and we add the viscosity in a LBM way, but we add viscosity in the shock. Okay, we're working on that, but this is the only. This is something. So far, we don't know how to do better, but we still get quite sharp profiles, and you see that we can get the right Chapman-Jouguet detonation velocities. I'm not going to detail this exactly because I'm running out of time. But basically, we extended this in 2D and now in 3D to do propagation of fronts. So these are two fronts of detonation, hydrogen, and we're varying. So this is a fake chemistry, it's one-step chemistry. We're varying artificially the Zeldovich number to show the classical cell-like pattern. I don't know if you all know this. The detonations, they leave patterns, soot patterns in front of them. And basically for low activation, for low Zeldovich number, this is very regular. And for high Zeldovich number, this is highly irregular. So, and then the pictures we usually see in papers look like that. And this is just the history of the position of these triple points. By the way, for hydrogen, this is usually obtained varying the Zeldovich number is usually obtained by varying the dilution with argon. Okay, I'm going to show a few more examples. I think I have 5 more minutes. Yes. So we're working in the chair in particular with our neighbors, which is a company called Fifth Pillar, and they develop a number of burners, big burners, not very sexy burners, to do all sorts of applications, but they always need heat, basically. And they're considering a lot of their clients are actually asking for developing hydrogen burners. And what they want is, of course, for the burner to be able to work fully hydrogen, but since they don't know how much hydrogen they're going to have, they also want it to be able to work with fully natural gas. And sometimes with things are even more dirty than natural gas. So it's not easy to make a burner that functions both for 100% hydrogen and 100% natural gas. So this was the objective of a recent thesis. And here you see that they have some experiments. So this is something like this, more or less, in terms of size, 25 centimeters, I think. Chamber is 2 by 2 by 6, so it's a small chamber for them, and 1 megawatt. And they have some measurements, and so we could compare the simulations with what they have. So these are some more illustrations, but basically what they were wondering was the effect of H2 dilution on the flame length, okay, on the NOx, and on radiation at the wall. So this is something we do with Jean-Louis. So I'm just illustrating because I'm getting to another burner, which is a bit more interesting. These are some quantitative results. So because it's a big chamber, they don't have many experiments, okay? But they have can compare temperature on the axis, which, to be fair, is okay. Especially, we're happy to have the right temperature at the outlet because it's mainly due to radiation. But we cannot be sure with this result to have exactly the right flame length. This is a bit better. This is the O2 profile on the longitudinal axis. And these are some results you see for NOx as a function of H2 dilution. So basically, by the way, this is getting back to combustion. When you increase H2, usually, if you're not careful, now we know more or less how to do it, but we usually increase NOx. So hydrogen is not that clean because you get higher temperature. Okay, last case I wanted to show you was a nice challenge that was given to us by another company, and they have so now it's a bigger burner, and they had some combustion instabilities. So combustion instabilities is a coupling between the acoustics in the chamber and the flame. basically you can get some strong thermoacoustic instabilities, very known for rockets. So it destroyed a couple of rockets, but it can also destroy this kind of burners. And they barely destroyed this part of the burner. So they wondered if we could simulate this. So they gave us their cases with mass fluxes, so we could validate mass fluxes, swirl level, final temperature. So the power of this burner is close to 20 megawatts. And they also had pressure probes for frequencies. And basically, so the instability occurs just by changing, so not the power of the burner, but just by changing the ratio between the different inlets, okay? So how we were injecting. And so this is what the burner looks like with big squares, because I cannot show it for the geometry. But basically, we're able to recover the stable, so this is the pressure field, and unstable cases. And if we look a bit further, I can see that the stable case, this is the variation of heat release rate integrated in the chamber. So you see that it's quite quiet for the quiet case. And for the unstable case, we have variation, we observe variation of order 40% of total heat release rate. So remember, this is a 20 megawatt burner, 20 meters. So it gets you get a lot of vibrations from that. And I'm not and at a very minimal cost. Okay, so this simulation costs about 8,000 CPU hours. So we can look also at the flames. And they came back because they were happy with the results, and they were a bit afraid because they were developing an even larger burner, so 50 megawatts, and now it's 20 meters. And they wanted to test beforehand if it would be stable or not. So this is what the flame looked like. Unluckily for them, but luckily for us, the nominal case turned out to be unstable. And so we had some more work. So this is the pressure spectra. You see that you get a very strong peak at a quite low frequency. Don't give the frequency. You can trust me. And this is a lower, another nominal point, which you see gives nothing, basically. And we're given for this study a white card to solve the problem. So this is the old geometry, and this is a small change that we proposed. And we're very happy that they made the change. I mean, they trusted this result enough based on the first study to make the change before constructing the burner, finishing the burner, because actually they had already constructed all of the outer parts. Okay, so conclusions. So LBM is not black magic. It's a numerical method. You can do a lot of things for reacting flows with it. We're also working on multi-phase flow these days a lot. This is a big part of the work. We developed a fully conservative version, compressible. So everything I showed with thermoacoustic instability, detonation, and so on is fully compressible. We also developed, I didn't mention it so much, but a low Mach version, low Mach number approximation. So that's when we don't want to do an acoustic study. Actually, typically, when we do a thermoacoustic study, we usually start with the LMNA version, which is the same version, and then we change the parameter and we go compressible. Does it go beyond Navier-Stokes solver? So that's usually a question that we see in LBM presentation. For me, no. Okay, let me be quite clear. We're just targeting the same equations, just different construction for the numerical scheme, but we're targeting at least with what I presented today. Is it worth it? Yes. So I think it's quite the calculations are quite cheap. The cases I shown today are all below 10,000 CPU hours. Okay, so if you divide it on 500 cores or something, which is classical, or 200, it runs in less than a day. And industrially, this is the target. Okay, industrially, if you, I mean, Airbus, Safran, and so on, they're happy to do simulation to assist the design, for instance, as long as they're less than 1 day. If they're longer than 1 day, they can still do it, but they would use it as a problem-solving simulation. So if you have a big problem and you want to understand, then you might do something which is 2 weeks or something like this. But if you want to use it at the design stage, then you need it to be a day or a day and a half. What's next? So we're working again on discontinuities a lot these days, multi-phase flow and radiation also. So I did mention it without mentioning it, but that radiation is also in the code. And I think I'm finished.
Merci beaucoup Pierre pour cette très jolie présentation. On passe aux questions. Guillaume, tu commences.
J'ai une question peut-être assez naïve. Je ne vois pas comment est-ce qu'on peut modéliser la turbulence en Lattice-Boltzmann parce qu'il n'y a pas de viscosité effective qu'on peut changer ou quoi que ce soit.
Si, il y en a une. Alors, justement, en fait, on fait comme, c'est vrai, pour presque tout, c'est pareil que d'habitude. Je ne l'ai pas mentionné. De façon très basique, ça c'est la forme la plus simple de noyeuse collision. Le taux là, c'est la viscosité. Et donc quand on fait la LES, en fait on fait un nu plus nu-t. Voilà. Pas plus. Il y en a qui font mieux, hein, mais là, le truc de base, tout ce que j'ai montré, c'est ça.
Est-ce qu'il y a d'autres questions, Rémi? Merci beaucoup pour ta présentation. Je vais te faire revenir tout à la fin. Moi, je suis plus acousticien que combustion. Et là, le tout dernier exemple m'a beaucoup plu. Comment vous avez réussi à enlever cette instabilité. Et j'ai vu apparaître les mots résonateurs de Helmholtz.
Oui, c'était un test, mais c'est pas ça ce qu'on a fait finalement. Ah. Ça, c'était... En fait, on a fait 4 essais. C'était leur dada en vrai. Mais on n'a pas mis ça. Parce que, en fait, ça... Alors, bah c'est celui-ci, le Helmholtz. Tiens, je n'avais pas vu que j'avais gardé les résultats. Donc, on avait... Ça, c'était la configuration initiale. Et quand on a mis les résonateurs de Helmholtz sur ce mode-là, bah, il a bien disparu, mais c'est un mode au-dessus qui est sorti. Donc, finalement, on a changé vraiment l'injection. En fait, en gros, on a changé un peu plutôt des retraits, et c'est plutôt des blocages de flammes. Enfin, l'endroit où la flamme... On a carrément changé l'emplacement de la flamme.
Ok, merci beaucoup.
Voilà.
Paola.
Merci beaucoup. Bah, c'est toujours très intéressant de voir les progrès faits par Lattice-Boltzmann vers de la physique de plus en plus compliquée. Juste un commentaire sur les comparaisons de toujours avec les solveurs Navier-Stokes classiques.
Oui.
Là, ce que tu montres, c'est essentiellement des problèmes dans lesquels les parois jouent un rôle mineur.
Oui.
Donc, finalement, disons que tu n'as pas à discrétiser des couches chimiques. Et j'étais intéressé par les cas que tu as montrés d'LM6 et de turbine LS89,
ouais.
Où c'est très haut Reynolds et les couches chimiques sont très fines. Donc j'imagine que vous mettez des lois de paroi
oui,
dans ce cas-là.
Absolument.
Et je me demandais, donc les estimations que tu fais en tant que calcul par rapport à Navier-Stokes, à isoprécision, est-ce que vous maintenez ces facteurs-là sur des cas avec des parois et avec des couches chimiques?
Ouais, alors c'est moins mon sujet du coup. Mais on y travaille beaucoup au labo. En fait, là, on est en train de tout reprendre sur les conditions limites. La réponse courte, c'est ça, on est en train de tout refaire.
Ouais. Après, vous aurez toujours
les lois de paroi.
On peut faire... jamais discrétiser une couche chimique à Y+.
On va jamais faire de la wall... On fait toujours de la wall model, ça c'est sûr. Parce qu'en fait, avec les petits cubes, bah, pas besoin de faire un dessin, on ne peut pas mettre de prisme.
De toute façon, les limitations associées aux fonctions de paroi.
Voilà, donc vis-à-vis de Airbus et Safran, ils ont l'air d'être contents des résultats, c'est ce qu'ils utilisent. Je ne sais pas dire beaucoup plus. Est-ce qu'on est, enfin, vis-à-vis de leur target, en tout cas, il y a plus de travail en ce moment sur comment imposer proprement la loi de paroi, l'aspect MATAP, que sur la loi en elle-même. On ne travaille pas trop sur la loi. En fait, il y a eu beaucoup de progrès qui ont été faits aussi sur les solvers Navier-Stokes type Octree, parce qu'il y en a beaucoup aussi, hein. Et c'est là-dessus qu'il y a le plus de travail. Donc en fait, on est moins précis, je pense, aujourd'hui, ça fait aucun doute. Par contre, là, on est en train de changer beaucoup de choses dans les...
Et une deuxième question, puisque tu montrais un cas turbo-machine,
Ouais.
ce qui est vital dans les turbomachines, c'est la conservation de la masse.
Oui.
Parce qu'une erreur, les turbomachinistes demandent une erreur inférieure à 1 pour 1000
Oui.
sur le débit. Et du coup, avec les méthodes de frontières immergées, c'est un gros challenge de conserver la masse.
Oui.
Donc,
Alors,
je ne sais pas s'il y a des progrès.
Si, on a travaillé beaucoup dessus et ça fait partie de la refonte. Donc ça fait 2 ans que, en fait, on a eu des vrais problèmes de crise avec Safran justement sur la conservation de masse. Donc maintenant, on a des méthodes qu'on est en train d'industrialiser là, qui sont conservatives numériques. On a les mêmes résultats qu'avant. Voilà, on est propre sur la pression et on conserve la masse au niveau discret. Donc c'est numériquement conservatif. L'endroit où on travaille encore, c'est là. C'est les transitions de maillage, on n'est pas encore complètement conservatif. Mais on y travaille, c'est un gros sujet.
Des interpolations à ce niveau-là, et les interpolations sont...
Exactement. Mais les parois, je suis content de dire qu'on ne l'a pas encore publié, mais que pour nous, c'est résolu. Enfin, les parois conservatifs en masse et en énergie. Enfin, adiabatique, si c'est adiabatique, et le flux thermique, il se retrouve numériquement dans le... Parce qu'en fait, ce n'était pas le cas au début. En gros, on imposait un flux et on n'avait pas la bonne énergie dans le flux. Mais là, maintenant, c'est le cas. Mais c'est récent. Très bonne question. C'est très récent et c'est très récent et là, on est en train de reprendre les transitions.
Une dernière question peut-être. Merci beaucoup pour la présentation. Ma question, c'est juste de manière un peu générale, comment tu fais du disphasique avec de la LPM?
Oui, alors c'est une très bonne question. Ben, on a passé 4 ans à faire... moi, je pensais qu'on allait faire des interfaces diffuses, parce que ça marchait pas mal pour un certain nombre de... Je sais que c'est pas forcément ce qui est fait ici, mais pour les applications que je visais. Et en fait, on a là, récemment changé complètement notre fusil d'épaule, et on travaille plutôt sur des méthodes d'interface libre, mais qui sont... c'est pas les mêmes qu'en Navier-Stokes classique, c'est vraiment très LBM. Donc basé, comme ce que j'avais montré pour les schémas, sur des échanges de masse au travers des liens. Et là, on commence à avoir des bons résultats. Mais donc en gros, le liquide, ce qu'on a, c'est une population pour le liquide, une population pour le gaz, avec des conditions au niveau de l'interface. Et l'interface, elle fait exactement une couche, quoi.
Il n'y a pas de problème fondamental globalement d'avoir une méthode qui est dérivée de la théorie cinétique des gaz
Non, parce qu'en fait, j'ai présenté... En fait, la LBM, on la présente toujours à partir de Boltzmann.
Ouais.
Mais en fait, une fois qu'on l'a construite, on ne voit plus du tout Boltzmann. C'est en fait, la LBM, il faut la voir comme une méthode numérique pour résoudre un jeu d'équations dérivées partielles. Et d'ailleurs, il y a plein de travaux sur... Enfin, il y a des choses dans la littérature sur... ils font de la LBM en finance, enfin, sur d'autres équations, quoi. Ça se fait. Donc après, il faut choisir le bon jeu d'équations. Et je dois dire que je pense que finalement, le jeu d'équations hyperbolique classique pour interface diffuse, c'est pas le bon jeu d'équations pour la LBM. Parce qu'une des difficultés, là, j'ai présenté des solutions pour la combustion. Une des difficultés, c'est que on ne résout pas forcément exactement avec le même schéma toutes les équations. Voilà. Et donc, quand on fait un solver classique, ben, en fait, on résout avec le même schéma toutes les équations. Et donc, les erreurs, c'est les mêmes. C'est ce que je disais là, donc il faut avoir les mêmes erreurs. Et en fait, on n'arrive pas. En gros, on arrive soit à faire de haut rapport de densité, faible Reynolds, soit haut Reynolds et bas rapport de densité, mais on n'arrive pas à faire les deux pour l'instant. Alors qu'avec les interfaces, là, c'est beaucoup plus prometteur. Ce sera pour une prochaine fois.
Merci.